Welcome to MathAlgo Studio, where math meets code. This is Computational Geometry series, designed to take you from beginner to advanced. You will see more than 200 plus videos on this series. In the previous lectures, we studied dot product and cross product of vectors and implemented them using C++. In this lecture, our goal is to combine dot and cross products to understand a powerful geometric concept called the triple dot product. In 3D geometry, many engineering problems require us to answer questions like: do three vectors lie in the same plane? What is the volume of a 3D shape? Are 3 points coplanar? So far, we have learned: dot product helps us measure projection and angle. Cross product helps us find perpendicular direction and area. But in 3D geometry, these are still not enough to calculate volume. So the triple dot product helps us answer these three critical questions in 3D geometry. This is why the triple product is a cornerstone in computational geometry. Now let's understand the triple dot product geometrically. We start with three vectors A, B, and C. First, take the cross product of A and B. This gives us a vector A times B, which is perpendicular to the plane formed by A and B. The magnitude of A times B represents the area of the base, which is this parallelogram you see here. Next, we take the dot product of A times B with vector C. So mathematically, the triple dot product is written as A times B, point C. Finally, two important conclusions. First is the result of a triple dot product is always a scalar quantity. Second is its physical significance, is that it represents the volume formed by vectors A, B, and C. We know formula for volume is that area into height. Magnitude of a cross B gives base area, and component of vector C is gives height, that is magnitude of C into cos alpha. Here alpha is angle between vector C and cross A and B. We are familiar with the expansion of dot and cross products of vectors. Keeping that in mind, we can express as according to the dot product of vector properties, the final triple dot product matrix is this gives us scalar value which is equal to volume of parallelepiped. One important note that if the triple product of vectors is 0, then these three vectors are coplanar in nature. Now let's take a numerical example to clearly understand the scalar triple product and its properties. We are given three vectors. A is equal to ij plus k. B is equal to 2i plus j plus k. C is equal to I plus j to k. First, let us calculate ABC. By definition, ABC is equal to A cross B into C. Instead of directly computing the cross product, we use the determinant form of the scalar triple product. So we write is equal to 1 1 minus 2, 1 minus 1 1 to 1 1. Expanding the determinant, we get answer minus 7. This negative sign tells us that the orientation of the vectors is reversed, but the magnitude still represents volume. Now let's see how the scalar triple product is implemented programmatically in C++ using the same example we did. I have written a function called Scalar Triple Product, which takes three 3D vectors as input A, B, and C. Inside this function, the first step is to compute the cross product of vectors A and B. This gives us a new vector called cross AB. Next, we take the dot product of this cross product with vector C. In the main function, we define three vectors. A is equal to 1, minus 1, 1. B is equal to 2, 1, 1. C is equal to 1, 1, minus 2. These are the same vectors we used in the mathematical example, so the result should match. Finally, we print the value of the scalar triple product by calling Scalar Triple Product A, B, C. When this code runs, the output is -7, which confirms our manual calculation.